Example number 2 in unsymmetrical fault, and for this example we have been asked to draw the positive, negative and zero sequence network for the following power system. So we have, this is the one-line diagram of the system, a generator connected to transformer number 1, then transmission line, then transformer number 2, and then connected to generator number 2 through a circuit breaker. So the positive sequence network will gonna be a ground voltage source going through the generator subtransient reactance, which is J.22, then the transformer, which is J.1, then the transmission line J.5, and then transformer number 2 J.1, then the subtransient reactance of generator number 2, which is 0.2, then the source voltage, and then it's grounded. For the negative reactance symmetrical diagram, it will be without the voltage source, and the same numbers are written, except for generator number 2, which gonna be 0.18, then it's grounded here. Now for the zero sequence network, we can see that this generator is solidly grounded, so you will have a ground here, then the the zero sequence reactance of the generator number 1, which is J.1. Then for the transformer is delta on this side, so it will stay open, and then solidly grounded on the other side, so it will be grounded here. Then the zero sequence reactance of the generator, which is 0.1. Then for the transmission line, it's J1.5. Then for generator number 2, since it's solidly grounded from both sides, it will be in series, J.1. Then for generator number 2, the zero sequence is 0.1, and then the neutral reactance, which is J.05, multiplied by 3, it's J.15. Then it is grounded, since this generator is grounded through the impedance. So this is the zero sequence reactance. The second part of this question is asking, he wants the fault currents due to a line-to-line fault or short circuit at bus number 3. So bus number 3 is here, so there is a fault here, so we need to find the generator's current, which is the generator number 2 current and generator number 1 current. So first of all, we have to find the Y bus of this one, Y bus of this one, and Y bus of this one, or we can, and then transform them into impedance, or we can find the Thevenin equivalent. So we have to find the Thevenin equivalent Z0 and the Thevenin equivalent of positive sequence and the Thevenin equivalent of negative sequence impedance. So let's go to the positive sequence network. The fault happens at bus 3, which is after the generator the transformer number 1 here. So the Thevenin equivalent will be, these are in series, and then it's in parallel, so it will be J.32 parallel with J.8, which is this plus this plus this, 0.5 plus 0.1 plus 0.2, and it will give me J.2286, and the positive sequence impedance is the same as this is the positive sequence, and the negative sequence is equal to the positive sequence, which is let me check out. No, it's not the same because we have here 1.8, so it's gonna be something else. J.32 in parallel with J.78, which will equal to J.2269. For the zero sequence, the fault is at this bus, so it's gonna be J1.5 plus 0.1 plus 0.1 plus J.015. So J point it will equal to J.9487 per unit. So to find the fault current, I fault 1 is equal to negative I fault 2, which is equal to the pre-fault voltage divided by Z Thevenin 1 plus Z Thevenin 2, and this will equal to the pre-fault voltage is 1 divided by J.2286 plus J.2269, and this will equal to negative J 2.1954 per unit. So to find the generator currents, I need to find the ABC current, which is the currents of phase A and B and C. And since this line-to-line fault, one of the 3 lines will going to be equal to 0. So this will be A times I012, and when I write I012, it's actually I0, I1, I2, and when I write IABC is IA, IB, and IC. So this will equal to 1, 1, 1, 1A square A, then 1A A square multiplied by I0 is 0 in line-to-line voltage. I1 is going to be negative J 2.1954, and this is J 2.1954. So what I'm gonna get is 0 minus 3.8025 per unit and 3.8025 per unit. So this is IABC, so IA is 0, IB is minus 3.8025, and IC is 3.8025.